And I might as well start recording it too. I forgot to record it last time as well because I started the stream first. All right. Is there sound now? Ask. Sorry? Okay, it works. All right. So, you know, it's like doing the same thing over and over again, and sometimes it works. Welcome to technology. We like reproducibility. All right. So this is an interesting blog. I'm not going to go through it here. I'm pointing you at it because it talks about classes and kinds of failures that are very common in distributed systems. Here's your dead cat. And of course, I moved the mouse, so now the remote mouse doesn't actually work. And this is my latest take on Murphy's Law. Just pretend it can't happen. And in some ways, that's kind of what we end up doing, because that's going to be the theme when we talk about FLP on Thursday. It's going to be like, well, you know, it turns out that in this general model, we can't actually do it. And it's like, well, we're just going to fake it. So just keep pushing. My learning goals for today's conversation with Finn is really about giving you some access to these tools. He's the expert. I'm not. I look at this stuff. I play with TLA+. I read this stuff. I mean, I've worked with various modeling tools before. They're very useful. And the reason that we use modeling tools is that it's really hard to build full-fledged systems. I usually joke that papers in the systems field are, we do stochastic gradient descent 18-month project at a time. And it's a slow, painful way of doing it. You sit down and you build something real on real hardware, and it doesn't work right, then you spend a lot of time debugging it. This is exactly what I saw when people were using the projects from the DS labs. They spent a little bit of time putting some code together they thought would work right, and then it didn't work right, and they spent a lot of time saying, why doesn't it work right? So the idea is, instead of building the system first, model the system, build a model of what you want to do, and make sure that your model, which is really more about your conceptual framework of what you're building, does it work there in the model? So this is a fast way of prototyping and figuring out if your model actually makes sense, if it actually works. And Finn's going to be talking about, because he's the expert here, he's going to be talking more about these tools and the mechanisms, and he's already warned us, it's some of the pitfalls, because it is kind of fake it till you make it in many cases here. You do the best you can, because exhaustive validation isn't practical given our compute resources right now. So the question I want you to be asking yourself when you're done with his guest lecture is, how could I use what he's talked about when I'm designing and building my distributed systems, because I want them to be as robust as possible. And so this is Finn. He is a student or candidate?
Student still.
So he's a student. That means he hasn't actually proposed his thesis yet, but he's getting there. He'll be there soon. He's a published author in this field. He's actually got a couple of papers, fairly recent papers, about modeling, verification, and so on and so forth, and he can tell you more about that if you're interested. And he then included this really cool video, which I've embedded, and we'll see if it actually works and if anybody at home can see it. If not, well, I guess I have to click over here, don't I? Not on the OBS Studio picture of it. Sound won't come through because it's muted. I've done this before. All right, you know what? Never mind. You can watch it on your own. He also gave us a picture. Next one.
Fortunately, the video actually has like about 150 views, and since I know no one other than you all will watch it, that means a lot of you have.
Good. Well, I didn't tell them that I was going to embed it in the stream, so we actually do have this picture that he gave me as well, and I embedded that. So I'm going to turn it over to Finn and let him do his magic.
All right. Can I zoom the picture in at all?
Let's see. That's a great question. It deserves an equally good answer. Probably not.
All right. It's fine.
It's PowerPoint, so.
Okay.
Can we figure? Oh, look at that. We can.
Nice. Cool.
So it's control mouse wheel up, down.
Okay. And can I drag it around at all?
Wait, you're just asking for it. Yeah,
Okay.
you gotta do left click and drag.
Cool. That's great. Okay, those were the two motions
Probably
I
won't even
needed.
need that.
Yeah. Right.
There's a laser pointer on it if you need it.
Thank you. Right, okay. So, yeah, hi, welcome to this session on the whole thing with formal verification generally aimed at distributed systems. I'm Finn. I said all this self-introduction part already in the video for the many of you who watched it. Thank you very much. It's my second video ever, so I apologize for several.
Are you sure they watched it? We should probably ask. Did anybody watch the video before they came to class? It wasn't too long, was it? And now you know he's crazy. There you go.
Cool. All right. But yeah. All right. So yeah, I'm glad that reflects the number that I saw. It could have been you all just clicked on it, watched 2 seconds, and that counts as a view or something. I don't know. Anyway, so yeah, here's the whole spread from the video. Can zoom in, zoom out, and drag, and that was what I was aiming to do. And I guess I'm not really used to these kind of discussion-style lectures, so I'm hoping to quickly speed learn how to do this right. I guess we can probably go level by level and just sort of see what sticks out to people. Oops.
Well, maybe we should start by asking if anybody had any questions, or was the video clear enough and you like walked away and said, wow, this is awesome and I really want to use this and I know how I'm going to use it with my distributed systems. I know that was a lot of long question.
Okay.
Did it make sense to anybody? Anybody have any questions? It's going to be a long session. That means you get to kind of poke and prod at them and tell them what you think is interesting.
Right, cool, yeah. I figured something to that effect. So I guess just as a starting point, because this is generally, you know, kind of a possibility, who among us here has actually happened to use the types of technique I describe in level 1? That being the sort of iterative exploration fuzzy approach where you just sort of try a bunch of stuff in an automated way. Who's actually ended up doing that ever? Oh, nice. Yeah, it's generally speaking, you'll see this, you know, start to pop up in industry. Like you'll go to an internship and all of a sudden they'll be saying, oh, check out this amazing cutting edge thing that we're doing. Cutting edge, lol. But hey, cutting edge for actual practice, where they're actually running through and generating all these kind of test cases. For instance, I don't think they'll sue me for saying this, but Arista Networks was getting into this 5 years ago, probably still using it, still doing stuff with it. Basically, for those who don't know who Arista Networks are, they're a company that manufactures the network switches that make sure that, you know, all those data centers actually work. So, to check that their things make sense, they'd actually run through and hit them with a bunch of like weird interactions and patterns and stuff and see if anything broke, and if it did, they'd fix it. If you have like high availability requires, i.e. Microsoft will sue you if your product breaks, this tends to be a very good thing, and people really do use this one. So I just thought that was a fun thing that came to mind. That primed anyone to have any further thoughts? You know, want to conduct any industrial espionage on Arista?
Just as an aside, Arista actually was co-founded by a UBC undergrad, David Cheriton, co-founder of Arista Networks, and he graduated here a long time ago. And he's donated money here. Not as much money as he donated to Waterloo, because they renamed the School of Computer Science after him.
Mm-hmm. Yes. I met him once. He told me I explained something wrong.
That sounds like David.
Yeah, I have a little tally chart of, like, every time I meet a senior person in the field and they tell me I got something wrong. Yeah, it's pretty funny. Well, at least, you know, that's how I choose to take it, right? Otherwise, it's like, oh my god, he destroyed my whole career, no! I mean, there's nothing to be gained from thinking like that. So, yeah. Any questions about anything I said, even the off-topic parts?
They're very shy.
Fair enough. Well, I can keep doing stand-up of... Oh, yes, go on. Mm-hmm. That's actually a really good question. I didn't really talk about that. You're right. So the simple answer is, for a lot of these plug-and-go fuzzers, the model is basically, does it segfault? In the sense of, really, the fuzzer doesn't understand very much. The smarter fuzzers understand some things about application control flow, so they can try and trigger, like, different branches of conditionals and stuff. But genuinely, a lot of the sort of stuff in, like, the level 1 area, like American Fuzzy Lop and that kind of group of, I'm sure, very many fuzzers that are more advanced than that came out since I looked at the area for related work research. Basically, their whole deal is you'll run them on something like libjpeg, you know, the thing that everyone uses to open JPEG files. It's written in C. If you can crash it, you've just broken, like, most web browsers. So your question becomes, all right, what can I do with it? And then they'll just sort of hit the thing with a bajillion, like, random byte streams with some knowledge of what they're doing to, like, the parser. It tends to over-exercise the parser massively. Like, half the things it does, it'll be invalid inputs. It doesn't even make any sense. And then some innovators decide to sort of give it kind of a grammar for what a valid input looks like. And then it does that instead, and it gets a bit further. And it's very much this kind of, what is the least I can specify, ranging from do it segfault to vague notions of valid inputs, such that I can get more bugs and publish more papers, and admittedly fix more potential security vulnerabilities in these very widely used tools. I mean, it's a valid approach. It does things. I mean, there are other ways to crash a program, but yes, you're right. C-type programs or very low-level code has a certain attraction to finding this type of issue that you might not so much run into. I mean, hey, if you tried this on a Java app, you'll be looking for other things, like element not found exception or null pointer exception or something like that. It's not exclusive, but I get your point, and if you can prove it statically, that's kind of like the bottom of the iceberg slowly creeping up into the design of our programming languages and being like, I mean, I am nowhere near, you know, most of the type checkers you will have are nowhere near as smart as half this iceberg. However, they're actually built into your programming language, and generally you don't have to think about them very much, and they'll answer simple questions with decent accuracy. It's great. See Rust, for example. That's a good example of some of these analyses.
I'm going to ask you a question.
Oh, go on.
And I'm going to ask it of you guys. How many of you use Windows? There's a pretty surefire way of making your Windows system unbootable by turning on a built-in tool that validates that all of the device drivers on your system are obeying the rules. It is literally a mechanism or a system of turning on invariant checking. And it's built in. You don't have to do anything. You don't have to install anything. You can literally just, like, fire up verifier, and I'm gonna step in here and be rude to our guest speaker and say verifier, and you can see it's actually a command. You can't see it, but he can see it, so you'll have to believe me. Do you really want to do that? Oh, I'm getting a UAC pop-up. There you go, driver verifier. It is built into the operating system. You can create custom standard, blah, blah, blah. And I know that if I go in and I say custom settings for code developers and I say turn it on for everything, it's going to cause all sorts of havoc because it will cause sloppily written drivers, which is most of them, to actually crash. And if you do it properly, can turn on things. You were talking about memory checking as an example. You can turn on failed pool allocation. So what do you do in a driver when there's not memory available? You can actually turn on a check, and it actually simulates memory allocation failures. Does your code properly handle memory allocation failures? And I had a bug one time where I failed memory allocation failure, and then I was actually looking at the crash afterwards, and it had failed 661,000 times before it hit a bug. I laughed and I said, well, it's actually not too bad. and then I fixed it, and then just life goes on. So you can turn all sorts of interesting things on there. And this is built into the tool. And this has been there for pretty close to 20 years. And one of the reasons they put it in here was because I didn't turn any of that stuff on. One of the reasons they did that was because this is a really simple way of finding and detecting bugs in people's code. And it's built in. It's not turned on by default because I can tell you that it's really uncomfortable when you try to reboot your Windows system and you get, well, it used to be blue screens of death and now they're just frowning faces of death. Oh no, something bad happened. And you can't reboot your system. You have to go into safe mode and turn it off. Literally, I've done that. That's why I don't turn that on a production. I turn it on inside of a virtual machine. But it is an example, as you were talking about that, I thought it was a really good example of exactly the kinds of tools that you can build. One of the tools that, Mark Rusinovich actually built a long time ago, got us into some trouble building it. But you may not know him. He's the CTO of Azure, worked for me years ago. And while we were working together, he built a tool. It was basically a fuzz checker. It would literally just send garbage to system calls and see what happened. And it kind of pissed Microsoft off. But at the same time, they also adopted that and ended up building their own fuzz checker. And then a couple of years later, we were working on it for them. And what we found was we actually found some drivers that were carefully using values outside the range that were being checked by the fuzz checker, because you can't check everything, in order to hide the fact that they actually had bugs. So fuzz checkers are real. They actually do find real bugs. We use them in real production systems because they improve the reliability. So even after you've built your model and you've validated your model, and then you turn it into production code, you can still go back and run these fuzz checkers. You can still run these kinds of programs to see if your implementation is correct. And that's an important distinction that may not have come through because, of course, Finn's talking about the verification side of it. But your model and your implementation are different. Your model is what you validate when you're doing formal verification. Your implementation can still be buggy as hell. And you still want to be able to test that and to be able to find those kinds of things. So sorry to interrupt, but you were talking about that and it reminded me of this. And it's easy for people to go off and try and go, oh, wow, I didn't even know that was there. How many people knew that about driver verifier in Windows? Pretty cool tool. It's a dangerous tool. Turn it on for, like your mom or dad's computer and see what happens. Oh, it shouldn't do that. Wow, that's a buggy driver.
That's a good point. And actually, while you were describing that, I remembered another interesting thing that I kind of skimmed over. I skimmed over basically everything in the video, so I can basically pick any one of these things and there will be so much more detail. One thing that's quite interesting and stands for basically every one of the iterative-y, checky parts of the sort of upper layers of the iceberg as I presented it, is the need to approximate things. So, for example, what I was discussing earlier, if you have your, if you're choosing inputs based on like whether it triggers control flow, that's one way to choose certain inputs. Because I mean, the most obvious and basic way to choose inputs is literally, if you'll know Wheatley from Portal 2, it's like 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, 1, 3, 1 billion years later. But like most of the combinations are not importantly different. And so what Tony mentioned right in the middle there is these fuzzers weren't trying everything. They were sort of picking and choosing interesting little bits they would jump around to try and fake trying more than they really did. Because, if you have a string of numbers, you can imagine, like, if this is a string of bytes, that's 512 values per byte times, to the power of the length of the string, you're going to suffer. So there's a lot of issues where you basically have to budget any way you possibly can. If anyone has used like Haskell Quick Check, it's got this whole strategy of like zipping around the state space. Like, let's try a really long list. Let's try a really short list. Let's try the empty list. Let's try lists with random junk according to some statistical distributions made by people smarter than me. Let's try all that kind of stuff. And if you try to actually try all the lists, your problem kind of changes shape. It's kind of funny. Because some of the checking mechanisms are about trying all the lists in a certain space, because, hey, if you get unlucky, you'll carefully avoid the bug by accident. So there's a different way of thinking about it, which is try, with a bunch of fudgery still included, try all the lists up to length 3, or something small, because otherwise you'll suffer, as I mentioned. But that's also another way of doing it. You can either sort of jump around interestingly, or you can prune your space by limiting things, and then it'll do all the funny edge cases with the empties, up and then a bit more. But if there's a bug that happens for a 500 element list, whoops. But hey, there's all sorts of different strategies and ways of, like, policies for figuring out which things you fuzz, and that's a whole area which, I mean, obviously someone's gonna say, oh, did you try putting machine learning? Yes, they tried. They tried it a lot. Yes.
So I'm going to ask a different question, and that is, how do we relate this to distributed systems? They don't really seem to understand what a distributed system is, despite the fact they signed up for a course to study distributed systems. I think it was just like, yeah, I got to fill something in, so eeny, meeny, miny, mo, and I'll just take this one.
Right, so I was getting quite sidetracked into the details of single machine, single-threaded fuzzing. So, right. Yeah, good point. Good point to move on to. Where distributed system? Basically, it varies in terms of how exactly you're going to approach it. The bottom line is, rather than having just some pure function that you give it an input, stuff happens, you get an output, instead you have to deal with concurrency and things being kind of out of sync and lack of knowledge. And a very simple way to think about it, see if I can grab my way over here a little bit. Woo! That's not how that's supposed to work. I'm back.
There you go. When you have the hand, just pull down the left mouse button and you can... The mouse wheel will make it bigger.
Oh, left, sorry.
Yeah, the other left.
Yeah, sorry. Fun fact, actually. I'm used to using a right-handed mouse with my left hand. So there is a certain degree of reasonability for why I had them flip, because normally, left mouse button is actually my middle finger.
Okay.
But anyway. Right. That's got us a bit closer. I'm not sure how. Yeah, that's sort of visible. And for those who saw the video, which is most of you, you'll know what that actually looks like, and you can always, open the video and pause it at the right place if you want. Okay, so basically, the simple way of doing this, which I think can be credited more or less back to Leslie Lamport, but I'm sure a few people came up with it, and different people posited different understandings of it.
How many of you know who Leslie Lamport is? Ever heard of LaTeX? The law is Lamport. We're going to talk about Lamport clocks. That's the same Leslie Lamport. We're going to talk about this cool island in Greece called Paxos, which is one of his papers. That's the same Leslie Lamport. He also created TLA+, which is a formal verification language that he uses for formally verifying distributed systems. You'll see this theme that comes up over and over and over again in distributed systems, and that is the name Lamport appears repeatedly. So he is not just a bit player, he's like got this long-term recurring role. The man is in his 70s, he still is actively working at Microsoft Research down in Seattle. So if you end up doing an internship with MSR or at Microsoft, you might even bump into him in the hallways. Or you might even be working with him. You never know.
Can confirm, last year he was my supervisor's supervisor for an internship. Yeah, fine, he's cool. Funny fact, actually, the law in TLA+ is not for Lamport. That's actually the temporal logic of actions.
Yes.
I like funny acronym stuff. Anyway, so kind of, I'm not sure exactly which paper it would have been or how exactly it was, because if you actually go back through the history of these papers, sometimes people kind of discovered or came up with ways of looking at things that today are just like, well, obviously you'd do that. But there's actually a paper talking about it like it's new, and then you realize, oh, I guess it kind of was new. Wow. So I can't quite remember how this came about, but now a pretty standard way of looking at things, lots of asterisks, lots of like sub-conditions, is the idea of this kind of state machine. So the problem, basically, is it's going one step further along than just input and output. So you've got, like, some kind of starting position, probably, whether you know it exactly, or whether you have some kind of abstract representation of it. There's a lot of ways of doing it. And then you've got to deal with, like, stuff happening in the middle in various semi-arbitrary configurations, and how to actually deal with what's going on, like who could be doing what could be happening at any stage. And the simple way to look at it is, at any point, something might do something. Each of these somethings may have a before and an after. These may not directly relate to the real physical and slightly relativistic, or at least, you know, communication delay related things that will happen. For example, if you have a machine on one continent and a machine on the other continent, you've got the speed of light, speed of electricity, speed of whatever you're using to communicate the two, like, you know, your wire with two cups on the end. There will be cases where something happens far away, and you will eventually learn of it, but there is literally no one truth in the world that you can actually see at any one time. This system, a thing happens and it has a before and an after that is universal, kind of goes against that. Again, it's not perfect, but it's pretty good. And there's this whole literature that I'm not sure if Tony will take you through, but it's about, you can take a system, and if you want to actually get a snapshot of what that system is doing, distributed snapshots is what I'm talking about, then your snapshot may not be strictly real. You will get a snapshot that describes a state the system observably could have been in, but it is possible that the system moved while you were snapshotting it. And there's all these techniques that you use, basically, to avoid getting, you know, those meme photos on the internet of, like, someone moved while the photo is being taken and now they've turned into some blurry abomination and, like, someone puts, like, bass boosts over it or something. Basically, there's a bunch of techniques so that you can see a coherent picture of what could have been without blurs, but the picture may also be wrong. But, like, not importantly wrong, not in a way you could have ever measured, because, you know, you got the message back, and by that point, it's kind of up in the air which way round something was. I guess what I'm trying to say is, this is not a perfect analogy, and it's very interesting how it is imperfect. But basically, how you do this on distributed systems is you have states, which theoretically represent a global view of everything that's happening, or everything you know about what's happening, if your thing is a partial observation state. And then you have transitions between them, which may occur in different ways. For example, if you have two independent machines doing two tasks, and you want to think about them as one kind of universe, you put the two states together, and every time something happens, either one thing did something, or the other thing did something. And if they are ever able to interact, then, well, I guess that no longer works, and you have to split it up. You have to, like, split the somethings into smaller somethings that have to happen kind of one after the other. And then they might both touch the same thing in different orders, and you can sort of break down what they were doing into smaller and smaller pieces. And oh wait, the list from earlier is getting longer and longer, and we're getting more and more exponentially huge state spaces because we're having to sort of examine, okay, if this one does, like, this little nubbins here, and this one sort of goes a little here, then this one bonks that one here, and then that one just moves along here, and what in theory could be described as two events that happened kind of at the same time, to actually analyze it, now it's like 50 events, and they're all happening in this complicated spider's web, and it's really confusing, but we have analysis tools, and honestly 50 isn't even that bad. But, you know, if you get into something truly like billions and billions and hours of computing time, I mean, I guess the funny part is, Tony a couple weeks ago was telling me about how he had this one simulation that he was running for, like, over a week to get results or something. Is it over a week, or is it? Yeah,
actually, yeah, something like that.
Okay,
it took quite a while.
Sorry?
It took a long time, and for a simulation, basically, that was like 5 or 6 years worth of execution time.
Right, because he was also running it in parallel, and you can parallelize these to some extent. It depends whether the states are independent and stuff like that. It's quite doable. And then you can end up with these distributed algorithms whose purpose is to analyze distributed algorithms distributedly. So, Yodog, I heard you like distribution, so I distributed your analysis of distribution. So now you can distribute while you analyze distributed systems. Okay, go on, I see a question.
Combinatorial, right? It's a combinatorial explosion.
Yeah.
So,
yeah.
No, combinatorial is higher than exponential, right? You look at the bounds, it actually is higher. It's insane.
I guess because it's no longer a nice regular sort of sequence, and it's more this kind of branching thing. But anyway, go on. Yeah? Right. Well, that's half correct, and I should clarify. That's a good question. Thank you. What I mean to say is, if the level of detail you're analyzing at is A, B, B, A, well, you're done. That's that. However, if you wish to analyze something like a memory race in C++ or something with like the weak memory model and all the pointer shenanigans and reorderings that are possible, then you have to actually name every single subpart of every statement that you care about to analyze it. And your analysis burden just exploded. Even without like explicit state space exploration, you still now have a very convoluted thing to deal with, and even being able to represent that as any model ever. We actually had a visiting student, my sense of time is messed up, so I swear it was just like either this summer or like a couple terms ago. It was called Shiny Dan. It was really cool. Dressed really fancy. But basically, his entire research was taking the C++ memory model and actually expressing it at all, other than like in the prose in the C++ standard, which is real and does exist, but does not a logical formulation make. He tried to actually build a logic for it. I saw the presentation. My God, his entire thesis is this thing. It's genuinely like 100+ pages of all these descriptions of all the formulas and all the relationships, leveraging all the work prior to his own work, and still taking that much to actually explain any of it. And it turns out, at dinner one point, he was describing to me how, I can't remember, one of the famous, like, if not this one, like, something like the Collatz conjecture or something, can be like expressed using weak memory model semantics. It gets pretty into the weeds philosophically, but yes, this is an example of one of the most complicated models I'm aware of for an extremely tiny, trivial thing that most of us have used at some point, if only just by taking 221 and using C++ once ever. Or, you know, 213 and 313, which have p-threads and stuff, which is exactly what you'd want to use that for. And just because it's running on the same machine doesn't make it ineligible for these distributed systems analysis tools. In fact, often they're quite similar. The analysis is in fact, often when you're testing distributed systems, you will spin them up on the same machine anyway. Then you can simulate the death and the communication and the stuff like that. Yeah. So a lot of these techniques can be applied to threading, and there's been a lot more work on the threading because it's a bit easier to deal with, because threads don't just up and die unless you specifically simulate that. So I guess that's the difference. Sorry, I think I've just talked myself into a bit of a spiral there. Come back. We need you. Oop. Okay, that's back now. Cool. But yeah, so that's kind of how you look at modeling distributed systems, generally speaking. I guess.
So how do you approach this?
Sorry?
So you want to, so let's say, you know, that you're one of these students who says, okay, I think this is really cool. I want to explore this. Where do I get started? How do I design my system so I can model it, so I can actually validate my model? Because I'd love to see some designs that actually had, you know, like a TLA plus specification or a Pascal description of the model that you're constructing. And it's a lot easier for design project 1 than it will be for your capstone project, right? because it's a much simpler problem to model.
Right, that's a good question also.
So for your information, Design Project 1 is a primary backup replication server with a view server to arbitrate, basically to manage the configuration.
Okay, cool, right. Funny thing, actually, for our evaluation of one of our tools, we have a very limited one of those, kind of. We kind of focused on a different one, so it's really not developed at all. Don't go try to find it. It's probably not going to help you very much. But, so basically, in terms of actual tools you can try to use, it really depends. I've linked quite a lot of them in the video description, and like Tony's little syllabus thing has quite a few of them as well. It really depends how you're going to approach this. For the implementation level validation ones, typically they integrate with some runtime or other. I know one, the Coyote one, that's for C#, unfortunately. I believe there are a couple from Java, but I don't know what happened to them or how public they are. It might just be something I heard about the Amazon Web Services folks doing that just never got released. So that's the unfortunate thing. I was also actually told as a correction, for example, that Modist, that you can see right there, that I knew this to begin with, but I didn't realize there was a better thing to cite. Modist was never public. You can't physically use it. It's just a paper floating around in the ether that describes how they did it, and in that sense it has value. However, there's also Jepson.something. I linked it in the description anyhow. And that is an actually maintained, usable thing you can go try at the implementation level to try and mess around your thing. I'm not quite sure how it works. I've mostly just been told it exists, and here's a link to it, and that happened earlier today, and I haven't really read it yet. So it may be that it's completely inapplicable to your project code. I don't know, but have a click, have a look through. That's one way to do it. However, most of these things, like level 2 onward, are not implementation level programming languages at all. They are other programming languages. So basically, if you want to do this, the sad truth is, and it's very fun for me, I love this, that's why I'm in the field, you have to learn at least one new programming language, if not multiple. These programming languages are often somewhat simplified, especially the distributed systems ones. They're kind of, built for certain tasks. They'll be either terrible or completely unusable for other tasks. So as a result, they might be somewhat simpler to use. Just to go through, so Pigo is the tool that I published, I myself and Diane and Ivan, my supervisor, and it has a whole author list. Go check them out, they're cool people. Published semi-recently. That one has this weird layer of 3 programming languages on top of each other, which has been a bit of a sticking point for interns that we've had. However, yes, really, it looks a bit like pseudocode, and you can sort of write out these assignments and these state space things. And Pigo has the ability to actually extract the thing, a bunch of Go code, out of it and actually try to run it, but it can also just explore it in the abstract. You just spit out one of those state machine graphs with like millions of nodes, and you can write rules about it. Literally using this temporal logic TLA plus thing, and you'd write rules to the effect of always this, eventually this, always eventually this, eventually when this, not this other thing, but not too much more complicated. Usually your rules can be summarized in like a couple of layers. Similarly, you can just write your whole thing in TLA+. I did that. That was the one other paper I have my name on, more or less. And there's actually quite a few tools for this. This is being promoted within Microsoft, and there's like courses. Probably don't want to get another course and go sign up for that. They're probably paid and for like Microsoft employees. But basically, in TLA+, you can actually write out definitions. It has a VS Code extension, which is pretty decent. I used it for like 3 months. It's nice. And you can just go through, check the thing, try to use it on a slightly powerful machine. Like a normal laptop will actually get pretty far. But basically, it's this interpreted programming language where the only interpretation mode is, okay, following these rules, elaborate everything that could happen. And you can do that. But you also have to learn TLA+. And that's a fun thing. You can go check it out. If you're good at learning languages, you might get pretty far. But as always, that is the caveat. For Alloy, it's actually quite similar. Recently, they even had a new version. I checked them out while I was preparing for this. And yeah, they have this whole thing. They've got a lovely visualizer, which shows you, like, okay, you describe a structure. What are examples of this structure? Here's one. And it uses this kind of logical reasoning-based technique where it's not so much that it's enumerating them, but that it is using a logical foundation of, like, this can be connected to this. So if I try to find a this and a this, I can exemplify this connection and show it to you on screen. And it's this whole other thing, and people have specified systems in that, and it's really great. In fact, honestly, Alloy might be more beginner-friendly in some ways, simply because its syntax is a little simpler, and it looks a little bit less like the inside of an academic paper. That's one of the weaknesses of TLA+, I would say. It has some truly arcane operators and definitional rules. But also, you're free to email me if you get stuck on TLA+. I have worked with it for and hey, I'd be happy to try Alloy with someone if they wanna. Like, you know, within reason. I have other things to do. I'm TAing 313 right now. But, you know, there's some resources, and often you can email people, not even necessarily me, other people for some help. There's mailing lists and stuff. These are all tools with communities, not the hugest communities, but communities of some appreciable size. As you go down, honestly, Daphne is a very popular tool. It's kind of the closest to a real programming language, I would say. And basically, you can write a bunch of, like, imperative, vaguely C-like code, but with a bunch of logic mixed in. So you'll be saying, like, for all this, or there exists this, and every time you write a while loop. Remember that whole thing about loop invariants that they made you do in that other course, whichever one it was? That. You have to actually write them every time, no exceptions, because otherwise it won't believe you that the loop terminates, it won't believe you that the loop does what you think it does at all, it won't believe you the loop does anything. It just sort of stops and says, please write the invariant. So, the basic idea is, you can also get a great deal of freedom when you just say, assume that this function does this. Don't ask questions, move along. And it will believe you, and you can just do that. So there's a lot of weird dev tricks you can do in these languages that are completely nonsensical if you're thinking from a regular programming language perspective, but it's kind of like it restricts you on one front that you expect to be able to do from what you're used to, and then it gives you enormous freedom on all these other fronts that you had no idea were, like, physically possible. And that's kind of like the mind-bending experience of exploring these other programming languages, which is what I'm here for, I guess, but yeah. Ivy, if you liked Prolog, Ivy is similar. However, I would discourage actually trying it, because I did, and it's stuck on Python 2.7, I couldn't even get it to build. So, yeah, it's a bit tricky. You might have some luck, but I think a lot of the authors have moved on, and it's a little fossilized. You know, that was published 5 years ago, and the sad fact is not everyone maintains their things. Who knows? Ego might bit rot. I'm still around, and we're still, you know, it's still there. But do beware that some of these things were like, oh, they got good results, and then you look at it, and it's like covered in duct tape and string, and you're just like, oh god, what is... Some of these are like that, and some of these are actually like tools with communities, and it's important to try and figure out which one is which. And if for some reason you want to try the theorem provers, I mentioned them in the voiceover but not in the text. There's Coq, C-O-Q, for rooster. There's Agda, there's Idris, not Elba. Idris, I think, is more so of an old project, wouldn't try to pursue that. Coq and Agda are massive, like, mathematics proving industry mainstays. So if you have a good mathematical background and you want to learn that language, there are excellent textbooks I can refer you to. However, you will get a graduate degree, whether you like it or not, in terms of material. So do beware. Anyway, so in terms of actual adoption, it's basically you can write your system, or something that looks a bit like your system, prove a bunch of stuff about it, explore stuff about it. Alloy, for example, is specifically known as a great prototyping tool, I'm told. I haven't tried it, so grain of salt, but... and then it will sort of interactively show you edge cases and things you might not have thought of. It's kind of, you know, a pocket calculator for logic. And if you use it like that, it can be very effective. But like a pocket calculator, it won't solve the problem for you. So one way or another, you're going to have to do it, and then you're going to have to build the system. Some of these things have ways of extracting code, but that is kind of still a half-baked area that I am actually working on, so it's a bit complicated, and none of them work super accessibly. Go on. Okay. Model checking outside of the implementation level stuff we started this session with, model checking in the logical sense will not save you from implementation faults. Like, you know, seg faults, other weird junk that happens at the interface level. All these logical model checkers, like if you do your thing in TLA+, zero help. What it will save you from is protocol edge cases. So if there's a thing that will happen 1 in a billion times in practice, it will find it for you in 5 minutes and show it you. If you've described something that contradicts that being possible, or requires that you do something about it that you haven't stated. That's the thing. It's basically a self-consistency check. Anything you can express as a set of rules that and rules about the rules, saying, given this set of rules, you will always stay in this kind of place. If that's wrong, it will try to find the counterproof for you and show it you. And many of these tools, even like the super abstract proof ones, are basically doing that. Even down to the point where you're basically writing a math proof and it's basically saying, okay, well, according to the principles I'm allowed to use in this domain, what you just said doesn't make sense. I couldn't figure out a justification for it. Please elaborate. And either you do elaborate, or you realize that this is physically impossible and you will never win, so you give up and you go look at something else and try a different way, because there are lots of half-proofs that look okay until you hit a certain point, and then they just bonk. Nope, no more. Doesn't work, can't prove anymore. So I guess that would be the answer. Anything you can specify, it will check for cell consistency. Anything outside of the immediate rule set, you're on your own. Unless you're using a fuzzer, in which case it basically exclusively tests the interface area, because most of the logic, you won't find it so easily.
So one of the things that you might want to note is the DS Labs is built on top of, as I mentioned, a discrete event simulator. It actually uses state space exploration as part of testing. Now, when we say state space exploration, what it essentially is doing is changing the order in which messages are delivered. And it does that in a pseudo-random way. And the purpose of using a pseudo-random model is, any of you ever used a random number generator in your language of choice? Most of them aren't actually really random. Most of them are pseudo-random. So they are using some polynomial computation to give you a really long sequence that looks like a random sequence of values. The benefit of this when you're doing simulations is it provides you with reproducibility, so that you can reproduce the exact same state that failed when you were testing it initially. The downside to this is it is in fact pseudo-random, so there are going to be states, and we can't search all possible states, there are going to be states that we don't get to explore. But it's a pretty good technique. It is kind of like a fuzz checker in that way. It just happens to be a reproducible fuzz checker. And it's a very powerful tool. One of the reasons that I wanted you to learn about these kinds of tools is not because I expect any of you really to use them. I encourage you to if you want to and explore that. But you're going to go out there into industry. And you're going to find that if you're working for one of the large cloud vendors, they are all using these tools, and you will be a leg up just knowing they exist. Maybe you're not skilled at using them yet, but if somebody says TLA+, you'll go, oh yeah, Leslie, I know about him. I learned about that in my distributed systems class. That's Leslie Lamport, not Leslie Nielsen. So, They're both pretty funny in their own way. So that's the reason that I want you exposed to this. It is really important for you to understand that when you go and you work at Amazon, they actually use mixed model formal verification. Typically what they'll do is they'll do like formal verification of small pieces, and then as they get larger, they'll use more state space exploration and fuzzing style models, because formal verification through exhaustive search of the space doesn't scale up. It gets way big, way fast, far faster than you can actually reasonably compute with any size computer. It's on that very fuzzy edge. I mean, combinatorial explosion is just mind-bendingly scary. You know, it's factorial, right? Yeah, it is factorial, right? Well, okay, it's n choose m, right? Which is factorials on steroids, right? It just blows up really fast because you take, yeah. For all intents and purposes, it doesn't make any difference because we can't explore exponential state space explosion either. And we know that every time we take a set and we explore its all possible states, that's 2 to the n. So every time we know that when n is an infinite number, that 2 to the n is a larger infinite number than n was, which that always melts your heads. Anybody in here study math? A little bit, right? Yeah. And I studied math, and so I love number theory. Number theory is awesome, but it also really screws with your head. I still look at the Cantor set, and to me, I look at the Cantor set and I say, that is absolutely beautiful. And Cantor was basically the guy who gave us the whole model of infinite numbers that we use today, and how he proved that there were infinitely more real numbers than there were rational numbers through a diagonalization process, which you would have to study if you studied number theory. So Cantor also gave us measure theory, and you probably haven't heard of measure theory, but I'm sure all of you have heard of applied measure theory. It's called statistics. So we can take beautiful things and turn them into nightmares. Statistics is just awful, and yet we use it all over the place. Great. Measure theory is basically how you measure the size of things. You know, how far away are things? I run into this a lot when we start talking about machine learning. Any of you interested in machine learning? Have you heard of vectors? Vector databases? They're all hot right now because, of course, you know, it's the ChatGPT and large language models and blah, blah, blah. The reason they use vector databases is because they allow us to quickly and efficiently find things that are close to each other. Well, it's easy for you to think about close to in a 3-dimensional space. And maybe you can bend your mind a little bit around a 4-dimensional space because we have a time element. But when we get into vector spaces, we're talking about n-dimensional spaces. And nobody really visualizes a 1,000-dimensional space very well in their own head. You look at it and you realize it's a vector. Well, how do you determine how far away or how far apart things are in a vector space? Well, that's really easy, isn't it? Right? You know, you just figure out what the Euclidean distance is, and that's one approach to it. And then we generalize that, and we say, well, you know, actually it could be like the way we measure distance on a map, which is what is called Manhattan distance, because in Manhattan, all of the streets are laid out on a grid, and you can only walk in certain directions, and it doesn't matter whether you walk this way or you walk this way, it's exactly the same distance. And that's a different metric. And this is how we measure things. We measure distances that way. And that's what Cantor gave us. And it's really cool when you go back and you look at this guy and you go, how the hell did you actually even think this stuff up? It's crazy. But it actually turns out we really do use it a lot. These kinds of spaces blow up. It makes it really hard for us to do exhaustive testing. And that's why when you're actually building distributed systems, how many of you actually want to work for Amazon, Microsoft, Apple, Google, IBM, Oracle, who else does big cloud? Dropbox, Netflix. And I'm sure you want to do that because the problems you'll be working on are really, really cool. and it pays really well. Which of those is the big deciding factor? Maybe both. What is the distance between these things? So knowing these tools exist will help you when you're in those positions of trying to build these kinds of systems and saying, you know, now I'm getting paid to do this instead of paying somebody else to tell me about this stuff. And I know these things exist, and by golly, I'm going to use your money, Mr. Employer or Ms. Employer, and you're going to teach me how to use TLA+. You're going to help me learn how to model things better. Why would somebody want to do that? Because every single failure I talk about, the real systems where I say this failed, cost someone money. And that number is way more than what you will probably be getting paid doing those kinds of jobs. So the reason they're willing to spend that kind of money is because they want to eliminate those very expensive failures. Amazon now talks about, 7 nines and 9 nines level quality services. When you start building on, you're part of a team that is building some new Amazon service, part of your concern is, how do I make this thing as reliable as I possibly can? Now that 7 nines, 9 nines, 5 nines, whatever that magic number is, always admits the possibility for conditions that you cannot handle. There are failures for which you will not be able to recover, but they better not happen very often, because if they do, it's going to be really expensive. And when you actually have service level agreements from these companies, if they're violated, it really means that that company doesn't make money for that period of time, and it costs them money. So that's why they're willing to spend the time to educate you, know that these tools exist. Walking into those situations, knowing these tools exist, and understanding what they offer will help you get ahead on those problems. These are hard problems. I know we're sitting here and we're talking about simple little things, but it turns out that concurrency, in general, is actually really hard for us to reason about. If you look at the Kleppmann videos, Martin Kleppmann has a really cool set of videos that he did when he was a lecturer at Cambridge, and it is really great. And his class was called Concurrent and Distributed Systems, because in fact, when you really look at concurrent systems or distributed systems, they start to look an awful lot like each other. And I've noticed that as well over the centuries. Literally, the computers we build today are distributed systems. They have a lot of fate sharing in them, but they're all about sending messages between different components in the system. When I was first studying computer architecture, we'd had interrupts, and they were latchable interrupts. It was basically just somebody put a voltage on a particular line, and everybody else could see, hey, there's an interrupt. Now, interrupts are messages. What? Our computers are just nothing more than networks, little networks sending messages around inside of them. The benefit of having it in a single box is that we don't have very many. The failure domain is fairly small, right? Is that I talked a little bit about fate sharing. And in the failure domain, when we're fate shared, everything fails together. The power goes out on your computer, all the stuff goes away. Not some of it sticks around. But the moment that we have two computers, they're talking over a network, they don't have that same fate. They're on the same planet, so therefore they have some fate, some level of fate sharing. But the network between them is now unstable. Each of those individual nodes is now unstable, and this creates that explosion. When the power goes out here, there's no state space explosion. The only state we're going to have to worry about is getting our databases back into a consistent state, which is why I tortured you with the first 7 chapters of Petrov. That's really what he's talking about. He says, this is the data structures that we're using, and we have to be able to restore those things back to consistency. Great. That's fine. Now, let's do something interesting. Like, how about if we spew it out over the universe and have everybody talk to everybody else, and we want to do exactly the same thing. We want to store consistency to our databases, except our databases are now distributed across different points in space. These tools allow you to reason about this, and that's the reason I wanted you to know about that. because I want you to be able, even if you can't use these tools, even if you don't walk out of this class, because we could spend the entire term just talking about using TLA+, and you'd still not be an expert at TLA+. But knowing the tools are there and understanding why you might be interested in using those tools will actually benefit you when you walk out this door at the end of the term. I mean, I've used some of these tools a little bit, but I have not done them to the extent that people like Finn do. This is still pretty cutting edge, but it is happening in industry. It's not going to happen if you go to work for a small company, probably, not unless they're very cutting edge and very tweaky. But if you're going to work for Amazon or Microsoft or Google, I can guarantee you that if you're working in distributed systems, you will be bumping into these tools. Amazon won't build services anymore that don't have formal models and do at least some level of formal verification. It costs too much money. They could spend millions, tens of millions of dollars training you and other people like you to be able to use these tools, and it's still worth the price. Sorry, I wanted to make sure that people understood why I was dragging them through this, because they're probably sitting there thinking, my gosh, this is more like studying databases than anything else. What am I going to do with this? What does it have to do with distributed systems?
Yeah. It just occurred to me, actually. I completely forgot to say, because I didn't have the assignments in mind. Speaking of how can you use this stuff, you already are. Yeah, that the assignment tester thing, that's not some like scaled down like dumb version. This is genuinely an actual application of like level 1.5. And that is valid. And you can claim, you know, you will experience that. You are experiencing that. And that's a thing that, like, that is like Coyote. If you go to Microsoft, that is genuinely a project they use internally. And you can just look at this and squint a bit and be like, oh yeah, okay, I've seen this before. And, you know, you might have a pretty big leg up, actually. Never mind having heard of it. You've literally used it for a term, or will have used it for a term. So just felt that was a fun bit to add that I forgot to internalize because I haven't done your assignments.
That's fair enough. I mean, they haven't read them either. So. Has anybody looked at, a couple of people have started looking at design at DS Labs Project 3, which is not numbered the same as it is when you go to look at the DS Labs website, but 0 indexing, 1 indexing, it's close enough. And I'm going to talk about it more next on Thursday, because there seemed to be lots of confusion. I mean, I was getting questions about implementing it. I'm like, you're designing it. You're not implementing it. That's why I'm breaking it up this way. I want you to spend more time thinking about the problem and the approach. This is not a sit down and, yeehaw, I'm going to code a solution at the keyboard, because that's going to give you the wrong set of skills. The right set of skills is to step back from the problem and say, what is the problem I'm trying to solve? What do I think a reasonable approach for this is? How am I going to validate that approach? This is a how am I going to validate it. The DS Labs gives you a set of tools that in essence provide you with a way of validating your implementation. But in fact, the implementation in the DS Labs is mostly just a model. It's not an actual distributed system. It's simulating everything. It's simulating the network. It's playing games under the cover and changing the order in which the operations are occurring, because it's changing the way that messages are delivered on the network. So in essence, all the DS Labs is a modeling tool. And it's using invariants in order to test your implementation. It's testing your model. You're already talking about it. The people who took it last term probably never walked away and fully appreciated that. And that's part of why I wanted to go through a little bit more of this time. I really want you to understand DS Labs is useful because it's teaching you modeling skills. It's teaching you how to think about the problems. But I'm making it very explicit this way. Design solutions, and then part of the reason I'm saying you don't implement your own design, you implement someone else's design, is because you're going to sit there and you are going to look at their design and you're going to say, this is a piece of shit. And somebody else is going to be looking at yours, and guess what they're going to be saying? Right, exactly. And so what's going to happen is you're going to realize this is not good. And then you're going to say, how would I make it better? Because now you have some skin in the game. Because you know you gave somebody else your piece of very bad cooking, and they gave you their piece of very bad cooking, and you're like, I have to get better at this. That's the reason that we're doing it. Sorry, I didn't.
All right, so that's actually a pretty good ending. In terms of anything else I had to say, yeah, I just want to highlight the thing about changing message orders just by delaying things a bit. Even if you're not faking anything, literally just putting a tiny, like, variable delay on all your messages. Normally, if you just run your system 1,000 times, there's going to be this extremely tight, like, curve of it always hit these exact timings. But then if you, like, just jitter the thing a bit, suddenly you're seeing so much more, and you'll probably hit half your bugs. That was cool. That was a nice thing to point out in terms of how these things specifically work. And otherwise, yeah, that's all I got. Feel free to try these systems, sort of. You don't have a choice. You are trying one of them. Yeah, and the other deeper ones are a bit more academic, and for some of you, that might be fun. Feel free to reach out. We have the lab Systopia. Tony is in it too. My supervisor is kind of like half on leave right now, so it might be a bit weird, but feel free to reach out, email him, email me. Sorry?
They had baby leave.
Yes, paternity leave. So, like, totally understandable why. He's not just, leaving me to fend for himself for no reason. But yeah, so if you are interested in grad studies, I guess I should do a bit of shameless self-promotion. We do a lot of things. This kind of little box, little cubby hole that I'm in is one of them. I think it's really cool, obviously. But yeah, there's plenty of stuff around. And if you don't, that's fine too. Yeah, thanks for listening. Thanks for checking out these things. I hope this is somewhat useful to you in whatever future you have, be it next week or be it in 5 years.
Does anybody have any questions? Anybody have any questions besides what's for dinner? Just don't eat their cooking. Cool. Well, that's going to be it for today then. And I will be back on Thursday, and you'll get to listen to me ramble on and on even more than I did today. We'll go stop the stream and...
Cool.
Don't worry, they turn off when I put them back in.
Cool. Sounds good.
That's it. Have a good one. Bye. Have a wonderful time.